We're now going to introduce what looks like quite a different topic, which is systems of linear equations. In fact, once we've got these things straightened out, they're going to help us a lot in our study of invertible matrices. Let's begin with the definition of a system of linear equations. A system of m linear equations in n unknowns, x1 up to xn, with coefficients aij and b1 up to bm, is a list of simultaneous equations a11x1 plus a12x2 and so on up to a1n xn is equal to b1, and then a21x1 plus a22x2 all the way up to a2n xn is equal to b2, and so on. So this should remind you of matrix multiplication. What's on the left looks like the result of doing a matrix multiplication, and that allows us to express a system of linear equations in their matrix form. The system of linear equations on the last slide is equivalent to its matrix form Ax equals b, where A is the matrix formed by the coefficients on the left-hand side, the aij's. Vector x is a vector consisting of the unknowns x1 up to xn, and b is a vector consisting of the coefficients on the right-hand sides of those equations. To see this in action, let's take the system of linear equations 2x plus 3y plus 4z is equal to 5 and x plus 5z is equal to 0. The matrix form would be Ax equals b, where A is this matrix here. Vector x would be the matrix consisting of our variables x, y and z, and b would be the height 2 column vector 5, 0. Another thing that we associate to a system of linear equations is an augmented matrix. If you have a system of linear equations whose matrix form is Ax equals b, then the number of rows of A and the number of rows of B are both the same. They're both m, the number of equations. So we can form a matrix by adding B as an extra column on the right of A, and that's called the augmented matrix. Now here I've notated this with a bar between the A and the B. Sometimes people will write a dotted line between A and B. Sometimes people will write no line at all between A and B. It doesn't matter so long as you remember which one you're going to use. So I don't care at all how you choose to notate your augmented matrices. So to continue with the example we've already been looking at, the system of linear equations 2x plus 3y plus 4z is 5 and x plus 5z equals 0 would have the augmented matrix that's formed by taking the matrix form of that equation and then concatenating A and B, putting B to the right of A. So in this augmented matrix, it's worth noticing that the first columns, so all of the columns except the last one, correspond to a variable. Here, the first column corresponds to my variable x, the second to y, so that you can see, for example, there's a 0 in the second row in the y column because the coefficient of y in the second equation is 0. The next column will correspond to z, and the final column will correspond to something different. That corresponds to the constants on the right-hand side of our matrix equation. We're also going to define the solution, or a solution of a matrix equation. A solution of a matrix equation Ax equals b is a vector consisting of numbers, we'll call it v, such that AV is equal to b. Now a matrix equation may have no solutions at all, or it may have a unique solution, or it may have many different solutions. If the system of linear equations in matrix form has no solutions, we call it inconsistent, and if it has at least one solution, then we call it consistent. Here's an example of a solution, just so we're clear what we're talking about. If we have a matrix equation 1, 1, 1, 1, x, y equals 0, 0, where the x and the y are variables, well, one possible solution would be this vector here. And in fact, there are infinitely many other different solutions to this system of linear equations. So the key difference there is that a solution must be a literal numerical solution to your equations. Finally, let's look at solving systems of linear equations where there are the same number of equations as there are variables, and the matrix A in the matrix form is invertible. If you have a system of linear equations whose matrix form is AX equals B, and the matrix A is invertible, then in fact there is a unique solution to this system. The reason for that is that vector V of numbers is a solution, or if and only if AV equals B. That's just the definition of being a solution. But then you could left multiply this by the inverse to A to get A inverse AV equals A inverse B. So certainly AV equals B implies A inverse AV equals A inverse B. And you can also go in the other direction, because you can multiply on the left by A to go from this back to here. Okay, but this second line is true if and only if V is equal to A inverse B, because A inverse AV just equals V again. So in other words, V is a solution if and only if V is equal to A inverse B. There is one and only one solution to this system of linear equations, and that solution is A inverse times B. That gives us a condition for solving systems of linear equations when the coefficient matrix is invertible.